All right, let's get started. So those who are online, can you see the viewing of the screen well? Is it trimmed or cropped? Right down. Is the screen good? Can you see the far edges of the screen, of the slides? Can you hear me? Oh, can you see it? Somebody in the chat, okay. Says yes. All right, so somebody said, just wanted to ask about attendance quizzes. They are not available for online courses after week 9. Oh, okay. We'll make sure that they are released. All right, so let's get back to CAP 6640. And so today we will continue with one of those odd tasks that is unified and multitask learning in natural language processing. We'll go over single task learning limitations, pre-training and transfer learning, question answering, DICA-NLP, which is one of the kind of approaches that we use for multi-task learning, as well as question answering networks, and then anti-critical training and generalization, and then finally summary and takeaways. So the hope by the end of this lecture, you will understand the limitations of single task learning in natural language processing, explain the role of pre-training and transfer learning in multitask learning, and then describe how diverse NLP tasks are unified in a single task, particularly using question answering techniques. Understand some instances of those multitask learning techniques, including DICA-NLP and MCAN, and then analyze concepts of anti-critical and zero-shot generalizations. Before I get started, do we have any questions about anything that we have covered so far? Okay, you don't have any questions. So I have one thing to add. In the final project, when you put your report, you are expected to put like a link for a repo that includes any artifacts that you have generated during the work on your projects. And that's going to be graded. So it has like 5% of the total grade of that one, 7% of that. So make sure that you are working on collecting artifacts as you are progressing with your project, and put them in some place that you can share, like as a link. Could be Dropbox, Google Drive, maybe GitHub. Yes, go ahead.
If the model that you were basing your research on shuts down instead of...
That's your problem. So you have to restart it. Yeah. So that's why we have like a semester to work on this. And so we have to kind of account for hiccups. I call them hiccups, right? So we have to account for it. It's not really particularly your problem. It's just like nature's problem, but you have to deal with it, right? So just like, you know, you do your experiment. Now, by the way, I recommend against having like, you know, a single run of a given model and then getting the results and reporting them. That is not a serious kind of work. So if you want to do like something that is scientific, then you have to do your run multiple times on the same prompt maybe, so that the state of the model is manifested in the output, right? And so, and then you get the aggregates maybe of that three runs. Come again? Okay. Yeah, I understand. And you know, I understand. I mean, like, I'm not talking about a specific case that you have. It might be, for all I know, it might be like irrelevant kind of feedback for your test. But if you are like, say, for example, quantifying performance, like, you know, how often a given model hallucinates, and then you give it the same prompt, but then the state of the model itself, the underlying state of the model itself, may change between the two different like trials. And so you want to capture that kind of dynamic or uncertainty in that. So maybe you want to average across like, you know, multiple runs. All right, so the artifacts are very important. So just make sure that you have the artifacts. We'll talk about other things as we go today about the project. So let's go over single task learning and their limitations. So far what we have learned in most what we have covered is single task. So for example, it could be storytelling, it could be maybe summarization, it could be this and that, many of them. So machine learning with feature engineering is the initial kind of step in most type of tasks. And so traditional machine learning models like SVM, decision trees, would require some manual feature engineering. They would require some handcrafted kind of sets of features based on some prior knowledge that is encoded by experts or domain experts. An example of that would be like in many natural language processing kind of tasks, you would use TF, IDF, n-grams, whatnot for text representation. And then you build a pipeline based on some handcrafted rules to give you something out of it. Great. This is like, you know, solving some problems. but is limited in the sense that it is very laborious. So then came deep learning for feature learning. And so deep neural networks have been used to automatically learn those features without having to specify them particularly. And so this eliminates the need for this manual feature engineering and figuring out which feature would be best for the given task, because this is in a way automated. And the neural network, when it is looking into features, it has its own learning component that kind of weight the features. Eventually, they're going to be numerical values. So weight those numerical values in some optimization fashion to give you a good representation of an underlying entity or object. Example is CNNs. We have shown that actually CNNs can be used to extract hierarchical features from images and text as well. We have done that in translation. And RNNs can be used to learn some sequential patterns in text, and flavors of RNNs like LSTM and GRU can be used to do the same thing and do some predictions in LLMs. Deep architectures engineering for single tasks. So custom models architectures are designed for a single task based on those underlying features that we have extracted using the deep learning models. And so this would be typically using transformers for natural language processing task, or ResNet, the popular ResNet for vision tasks, including images. This in turn would require heavy tuning and task-specific modifications. Examples, you can use BERT and GPT style type of models to optimize certain structures for text generation and text understanding in general. So this is great, but it would work only for a given specific task. So it's like a single task. So if you want to do this for translation, you do it for translation, and that's it. You will not be able to do that for sentence analysis, for instance, using the same structure, the same tuning, the same learning. Okay, and this is a problem. So what is the problem? The problem is that effort is invested only on a specific task. Is that a good thing or a bad thing? I mean, it's not necessarily a bad thing. You can get a lot of it. You can also perfect this task, but it does not serve the general usage, utilization of those techniques and effort for what we want to do with NLP, right? So you want to do multiple tasks with the same learning capability, okay? So some of the issues is what we just mentioned. And so what you want to do next is you want to generalize AI models that can learn across multiple domains, multiple tasks, multiple models learning. You want to be more efficient in utilizing architectures for multiple contexts, and so that you can reduce the computational overhead, the computational cost. And you want to utilize maybe something like a few shot or zero shot learning, so that you not have to have this type of manual, handcrafted type of rules, or even labeled entities that you can utilize for building your system. And maybe you want to do something that is even beyond, that is self-supervised learning to reduce the label data dependency. So this gives us an idea of the evolution that we have witnessed. This is not something that we invented. It's what comes next from those two different approaches, whether it is handcrafted or deep learning-based feature generation. Okay, so eventually you have done this, and you have done this very beautiful fine tuning for a given task. But dealing with single tasks is going to be always limited. We mentioned part of it. So what are the limitations? Significant progress in ML with better data sets, models, and evaluation metrics gives you some great ideas, and optimized performance for specific tasks like in vision or speech is also something that is commendable, is great. It solves some problem, but it creates some other problems. So what are the other problems? Well, the first of which is, and the most significant one of which is the local optima problem in single task or task-specific models. So meaning that if you have, say, for example, a certain task, say, for example, translation, and you tune your model in a way that it would perform very well with respect to some given metric for translation. What kind of metrics we can use for translation? What kind of metrics? Blue, right? Or meteor or whatnot, right? Some overlap from between the source and the target. So it performs very well. And this performance, the good performance of this is a result of the tweaking of the parameters. And those parameters would just be very specific to the given task, but will not generalize. And the reason is because it would hit, you can imagine that performing on multiple tasks, for example, generation and translation, because translation can be done as a generation task, generation and translation would in a way, try to optimize for both tasks. And that is what we call a global optima for the parameters. When we are like working with a single task, what you are like really doing, or might actually be doing, is that you will really hit a sweet spot for this particular task, but that is through some local optima, okay? An optima that would not generalize for the other task, okay? This is what we call the local optima problem in task-specific models. And so models excel in specific benchmark, but fail to generalize beyond that benchmark in other benchmarks for the given task, or even beyond that given task for other tasks. When the set size is very manageable, less than, say, for example, 1,000 instances, you can optimize for performance. You can like tweak as much as you want. But the issue is that when you have larger number of entities beyond 1,000, then this becomes an obvious cost burden. And the issue, improvements are oftentimes incremental and task bounded. So we need something that is more than that. It's going to be the general AI. So you need continuous learning instead of training separate models per task. And a single model should adapt and retain knowledge and transfer learning across those tasks. And the current model typically would start with some random initialization and then partial retraining or pre-training, and then have like this lifelong type of learning. Okay, so this is what we want to achieve eventually. Any questions? All good? So we need to have multiple tasks. That's a simple answer. Like learning from multiple tasks, okay? All right, so let's go over pre-training and transfer learning as a type of capabilities that we can use for this particular direction, okay? So what is pre-training? What is pre-training? What did we have mentioned pre-training in this class? Pre-training, word vectors, for example. You have like a large corpus of data, and then you create vector representation for words. And then these are like quote-unquote pre-trained words from a general context, from Wikipedia, for instance. And if you want to use them for like, you know, your own kind of application, let's say cybersecurity, or you want to do it for medical, then you get like a few samples in that domain, and then try to fine-tune, tweak those representations to capture the new application space. So this is what pre-training. Okay, so the power of pre-training. So pre-training allows models to learn general features, general language features from large data sets before fine-tuning for the specific task. This could be medical, could be security, could be whatnot. And this creates some improvements, right? So you can imagine that the cost for running the given task, NLP task for medical, is going to be very little, very small, because you need small amount of data so that you can fine-tune your pre-trained model and then do whatever you want to do with it. And the same data set can be used for cybersecurity, can be used for aerospace, can be used for whatnot, okay? For whatever you want to use it for. So this is significant improvement in performance and reduce some the need for a large amount of labeled data. Success in computer vision, for example, for this particular application. We know the success in NLP, right? So we know that pre-trained models like word models and whatnot, they are like great, like Word2Vec, GloVe are some examples. We have Cove and Elmo and BERT and GPT and T5. All of those are very nice kind of pre-trained models, and you can easily customize them to do multiple tasks. By customizing, I mean you can fine-tune them. And this is not really limited to natural languages. You can do that also with images. So there are some pre-trained models for images. For instance, we have ImageNet pre-training, which kind of improved significantly vision tasks and was a breakthrough in that space. We'll talk about that when we talk about composition. We have common crawlers or CCs, which further enhance large-scale vision applications. And the sets and classification was the key bottleneck task in this domain, and it was broken with those advances of large amount of data that is pre-trained. Okay, this is great. So you can do a lot of good things with it. And so here's the application that we have. So for example, in Vision, why this like really was helpful in Vision, and why this is not really easily translated into NLP, natural language processing, in the text sense, is because we have a bottleneck in images. What is the bottleneck in images? What is the bottleneck task? That if you solve this bottleneck task, then you can solve pretty much every image application. What is it? Anything funny there you can share with us? No? You cannot share it with us? Then laughing is not maybe appropriate. Yes, go ahead. Huh? Object detection. No, there's more fundamental one than that. Image tasks, yeah. And feature extraction. No, something above that. Above that. You were saying something? Segmentation, no. Huh? Age detection, no. This is very specific. No, higher level, like something that is broad. Classification, yes, classification. Many of those things that you are mentioning can boil down to classification. And there is a bottleneck, right? You need to do like classification. Like, is this a cat? Is this like a monkey? Is this like David? So you have to like, make your judgment about objects, right? Come again? Ambiguity in images. And like everything that you mentioned is good, but it's not like the core tasks that if you just solve this task, then you can like comfortably solve a lot of tasks in the image domain. And so in vision, you have like this application. So you have a pre-trained system that accelerates downstream tasks. Vision had a clear task, which is classification. And once you solve it, then multiple tasks can be done. You can do like object detection. You can do maybe image understanding. You can do segmentation with classification, a lot of things. Modern AIs relies on large scale pre-trained and transfer learning for efficiency. And this is like, kind of solve the problem in the image domain. The problem with the NLP is that, like, for example, here's the example that we have here. You start with like encoder, decoder with some word vectors, and then you do some translation. This is the one task, right? And then another task, you have like, for example, text-specific model, you have word vectors, encoder, decoder, and you can do some task-specific model and say, for instance, this one can be sentence analysis. Any relationship between them? Not much, really. You are using encoder, decoder, but you are using them differently. So there is no bottleneck task that you can, once you solve, then you solve the fundamental problem in NLP. Make sense? Okay. Well, there is some abstraction that we can use. That's why we are here today. But that abstraction has nothing to do with a single task like classification. Okay? It's about formulation. Into a single task with additional context. Okay? So this is eventually what we want to do. And we will see that context in, say, for example, Deka NLP. All right. So why is NLP complex? Well, NLP requires multiple types of reasoning. So for instance, you have logical, linguistic, emotional, and visual. That's NLP. That is not in images. Short and long-term memory needs. Also, understanding a sentence requires short-term memory. Basically resolving pronouns in a paragraph is one example. We had that last time, right? With NER or with coreference resolution. And comprehending an entire document or conversation needs long-term memories that are not particularly specific to the given image. So this is like a distinction. Also, another challenge is the fragmentation of natural language processing tasks. So NLP has been divided into what we call intermediate and separate tasks like parsing, NER, and question answering to enable some incremental progress. Because if you think about like question answering, it is much more tractable of a problem than thinking about question answering in the context of, say, for example, coreference resolution or NER, right? So that was like one reason. And so the progress in this domain has been incremental and has been fragmented, okay? And so this led to benchmark chasing, where individual subfields will focus on optimizing task-specific models. And so with this fragmentation, what would work in one domain would not work in another domain as compared to, say, for example, images. AlexNet, for instance, has been used for pretty much everything. It was like 2009, 2010, and they made the breakthrough and has been used like until today. You can still see it. ImageNet, AlexNet, they've been used for that. So the question then becomes, can a single unsupervised task solve NLP tasks? All of them. The answer is no, because we know that they are different. So unlike vision, where self-supervised or contrastive learning can be used to do some representation and then do some classification, this is not the case in languages that require supervision. Again, the underlying reason for this is that a human learn languages through some feedback loops like interaction or correction, whereas the images do not have that. Also, understanding meanings depends on context or external world knowledge that is not an experience that is not necessarily represented in the given text. So text in general is more contextual than images. Like if I give you an image, it's like a boy and a kite and like blue sky and whatnot. Does not require any additional context to understand and interpret that. But if I give you a sentence, that sentence does not carry much of a meaning without the context that it has to be with. Okay. All right. So this adds to the challenges. Okay. So the key challenge in multitask learning is the blocker for learning in NLP. So it requires solving diverse tasks like translation, summarization, reasoning, question answering, whatnot. And traditional single task models would not fulfill that kind of requirement, would not generalize beyond training objectives. And that gave us the need for the MTL or multitask learning, which is essential for this, but remains a major challenge. Even with things like GPTs, multitask learning is still would require some effort, right? Because we know, like with prompt engineering and whatnot, you try to make LLMs work like nicely for a given task. Okay. Questions? Yes. 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 Next word prediction would not solve all NLP tasks. For instance, how would it solve just like as it is, like, without, for example, if you have next word prediction, it trained for generation, for instance, generation. How would it solve sentence analysis?
You have a like the and then
you will have to tune it.
Just pick one.
That's what we will do with Dika NLP, right? That's what we will do. We'll add that additional context. So that context has to be embedded into the task formulation, but cannot be done with the traditional way of doing things, that you have a model that is built for a specific task, and then unsupervised, it will solve the problem at hand for another task. Make sense?
But you put that in the
yeah.
But
yeah. Oh, that's what we'll talk about. They'll talk about it in a second, right? We'll talk about that with intercurricular and curricular training. Okay. So we'll have multiple tasks in a way optimized together. You will not have a perfect outcome for that. And this is like what we call multitask training. But in a way that is not unsupervised, it's supervised, still supervised. Okay. All right. So the promise of unified, the premise actually, the premise of unified multitask models is that instead of training separate models for each task, a single model, this is what we're talking about, a single model can decide how to transfer knowledge across domains and use the domain adaptation, weight sharing, and transfer learning and zero-shot learning to kind of perform on the specific task, okay? In a way similar to what we have with GPTs. Make sense? So advantages of this unified multitask learning is faster adaptation to new tasks, simplified deployment, lower barrier to adoption, and that it gives you the ability to do some continual learning. Okay. So how we do this? We want to express many NLP tasks in a single framework. And so to create that general model, different tasks must be expressed in a consistent way. For instance, we can use sequence tagging. So token level tasks, each word in the input is assigned a label. And this can solve problems like NER or aspect-specific sentence analysis. So those can be grouped down to the same task, the same type of task, like multitask, but the same type of structure. And then the output itself will be decoded for the specific task. Make sense? Good? Okay. So you have, like, for example, an NER, what you want to do is that you want to assign a given label, type, named entity, type to the given entity, and there's going to be a label. In the case of sentence analysis, for the given span, chunk of utterances, what you want to do is that you want to assign a label. That's another label. It's going to be positive, negative. And so you can view that's the same thing, but you're just increasing the span. Text classification, like sentence level tasks, you assign a single label to an input task, like, for example, dialogue state tracking. You predict the current state of the conversations, like intent prediction. For sentiment classification, you determine whether a sentence expresses positive, negative, or anything in between. For sequence models, like generation tasks, what you can do is that you convert an input sequence into an output sequence. There's going to be mapping of an input sequence and some representation to an output sequence and a different representation, and perhaps applying a layer of decoding on top of that. Okay. And so in machine translation, you translate text from input language, like one language to another, input language to target language. In summarization, you generate a concise summary for the given input that has some overlap with the input semantically and syntactically. For question answering, you produce an answer for the given question, and we have talked about that in multiple flavors. In this case, you can do that with generation, okay? So why that? Enables multiple tasks, reduces task-specific engineering, and moves NLP closer to generalized type of AI systems. Any questions? Okay, so all of those are great, right? You can have like, 3, instead of having like 10 tasks, you can have 3 tasks now, and they can generalize. Go ahead. Yes, please. I like fundamentals. Okay, so let me tell you like why. So for example, we have the same text that we want to train with, and we have that text for, say, example, the Wikipedia corpora. And we want to use that for sentiment analysis, training for sentiment analysis. We want to use that for training for NER. We want to train that for question answering. Okay, how many trainings do you have to do? 3. Imagine that you want to do a model, you want to build a model that can address all 3 tasks. So you start with like, a general task, and then you tune it jointly with the 3 tasks once. It's going to be like, maybe 1.3x the training for a given task, but not 3x, okay? That is one thing, okay? That's one thing. That answers the fundamental cost function. The other thing is that you'd hope that this training, joint training, will give emergence to a 4th task, 5th task, 6th task performance on the same data. This is what we call emergence of capability. So you'll have like a large number of parameters. We'll talk about that at the end of the class. When you have a large number of parameters and then you are playing with those parameters, some latent capabilities can emerge, and you will be able to solve, like, for example, something that is close to sentence analysis, like, for example, sentence tagging. Okay, right. It's a good question. And by the way, I did not sleep last night because I had an interview today morning for the Associate Dean for Graduate Studies. And so, like, give me fundamentals. Okay, all right. coffee speaking. Huh? I don't know. I mean, like, they said like they like me, but I don't know. It's not about like whether they like me or not. It's just a political hierarchy. It's recorded. It's, yeah. All right. So let's not go there. Let's keep here. All right. So I prepared for this one like I'm preparing for an exam, like a whole week. And I wrote my answers, and like, I was like, okay, so what if they ask about this? Everything that they asked was there. I've done a lot of interviews in my life. I'm 45 years old, and I've been doing interviews every other year for whatever reason. And everything that they asked was there. And so like I was like, yeah, gotcha. Yeah, I prepared for this. I'm not like my students. I give them the questions, they come here and get like 80. You gave me no questions, and I still like did well. Anyway, so being prepared is the secret to success. But it does not say anything. I don't know if I'm going to succeed or not. Language modeling can be broken down into 3. It can be like can be framed as 3 different orthogonal, not orthogonal, related tasks, we would say. And so we can, in NLP, generally speaking, we can frame anything as one of the 3 tasks, but those are actually translatable from one to another. Make sense? And so what are those tasks? Let's go back. What are those tasks? And what would be your pick for the super task? Like a task that you can use to translate any other task. So what are those tasks? Give me 1 or 2. Just random. Go. I'm going to put the slide. Yeah. What are those tasks? Okay. So we can have modeling, like predicting the next word. And so the example, we have, like, say, for example, the cat sat on whatnot, and then you have to fill that, like the mat. Okay. What is equivalent? It encodes like word knowledge and context plus for the downstream task. Another one is QA. All right. So QA, basically, you are given a context, like a pretext, and then you are just generating a response based on that pretext. Right. So example that we have here, Marie Curie discovered radioactivity, and by the way, she died because of radioactivity. Right. Do not mess with those things. And the question was, what did Marie Curie discover? And then the answer would be radioactivity. So you have like a given context, and you're given a question, and then you answer the question or like do the following, turn following, based on the context, okay, factual. And then finally, there is the other kind of equivalent task, which is dialogue. To generate context-aware responses based on some conversational history. This is like similar to the question answering, but it does not have to be a question. It can be just like a pretext, okay? So example, tell me about Marie Curie's in the system. She was a physicist who discovered yada. Why is it equivalent? Again, conversation agents require both language modeling and question answering skills to generate this, and so those are related. And so a unified kind of model, like say, for example, GPT or T5 that can be used for these kind of tasks, perform well across all three tasks. And that is because they are related. And this would blur the distinction between those different tasks. Make sense? Now, if I ask you, let's get rid of everything else and just like make it as a single task. What single task among those is going to be the super task? Huh? Language modeling. Okay. Anything? Any other thoughts? Generation. Okay. Generation is fundamental. Where is generation here? Huh? We have dialogue. We don't have generation. Generation is like way more fundamental. So we have dialogue. These are tasks. Dialogue. We have question answering, and we have modeling. Okay. Generation is part of the modeling. I think, because I saw the slides, I think there is going to be question answering. And the reason is because you can always shove down something along the question to give it the context so that it can do generation, it can do whatnot, right? Using some underlying engine, okay? Oh, something underlying, but not necessarily like language modeling. We can use like, something different, and we'll show like what is the different, okay? All right, so we have this. Okay, so forget about this. So these are the three equivalent NLP tasks, and so we have language modeling, predict missing context, missing or next word, and this is the example, encodes world knowledge and context. Question answering, given a context and a question, you answer, and what it does is, like here's an example, what it does is that requires contextual reasoning, similar to how language models fill in the missing slots or information. And dialogue, generate responses based on some conversational history, like turns of dialogue. And then here's the example. It combines elements of LM, language modeling, and QAs. Okay? Any question? Any questions? Yeah. No. Dialogue is some part of question answering, right? We can argue one way or the other, but like the way that again, these are conventions, like how people like in this domain have framed things, and so you can't always frame you can frame one or the other, but like the way that that dialogue is a smaller type of space compared to the question answering, and it does not have to be necessarily like a question that you extract knowledge based on. It can be the question itself that just takes a turn. Make sense? Yeah. All right. So let's move on. So multitask learning, question answering. So it's a unifying NLP task. Many NLP tasks can be framed as QA, and a unified QA-based approach will allow for better generalization than, say, for example, generation. Okay. What are those kind of tasks? Like, for example, we can do a QA from QA. That's going to be simple, direct, right? We can do machine translation. So the question would be, how do we say a given sentence in French? And the answer would be translation. Make sense? It's like how you make a question out of that. Summarization, question, what is a summary? And then it'll give you the summary. A natural language inference is going to be, does sentence A entails sentence B? This is inference. Similarly for semantic classification, semantic rule, labeling, relation extraction, REs, dialogue, semantic parsing, and common sense reasoning. Common sense. Common sense is 2 words, right? Or common sense? Is it 1 word? 2 words, right? Typo. All right. Any question? Another concept, again, like, here we talk about terminology. So one concept that we have is what we call meta-supervised learning, which is basically what you do in this space is that you extract supervision with the task description. And so because we want to represent all those tasks in a single task, which is question answering, we have to provide some additional information in the question that can signify the task. Fair? Is that fair? Okay. So you expand the traditional supervision from, like, say, for example, X, Y bear, and the task is to basically find out Y given X to X, T, Y. Okay. So you add this additional thing called tag, T. Okay. So X is going to be the context input needed to answer the question. In this case, for classification problems, it could be the input sample. And then T is going to be the task or explicitly defined as a question or Q. And then the Y is going to be the answer. So when you train, you do not train only with X and Y, but we know how to train with X and Y, right? So for example, in translation, how do we use X and Y? We build an encoder decoder, right, with X and Y's and try to reduce the loss. Here we have T. T is going to be the task specific. So we are optimizing for the given task here. And you can imagine multiple T's here, different T's. For example, they can be summarization, can be generation, can be whatnot. And then try to optimize for all of them. It's going to be question answering, but it's optimized for multiple tasks. Okay. So the key idea, using questions as task description instead of relying only on some structured labels, you frame the task as a natural language question, Q, and the model will then generalize by leveraging the linguistic information in the Q to connect tasks. Here's like some kind of ideas that how we can do this. Like, for example, in sentiment classification, this movie was amazing. It's positive. And the task would be, what is the sentiment of this review? And the context is, this movie was amazing. So you create a Q question, you create the context, and you hope to get the answer for the sentiment, positive, negative. Similarly for all other things, like, named entity recognition, for summarization, and so forth. And this is very powerful, right? It looks like dumb, right? It looks like dumb. But this is like, how people start thinking about multitask learning. And believe me, some very influential papers are there about this. We'll talk about one of them in a second. Okay, this is the one that we'll talk about in a second. And the reason why I still want to teach this, despite having LLMs and all that kind of cool things, is because I drew the figures by myself. Okay, and so if I spend like a whole day drawing a fancy figure, then I'll have to teach you that, even if it's like archaic kind of knowledge. Like, I don't know what is like the falsest type of theory, right? Anybody? Like in psychology, for example, I would like, teach you, who's the crazy psychologist out there? Freud theories, right? I'll teach you that if I had to draw something about it. Huh? Yeah. Never mind. All right. Freud. No, I mean, like, whatever, psychology. I don't know why I said psychology, but like psychology. I don't teach psychology, but like if I had like any drawing that I had spent like, a whole day doing PPTs, I'll have to teach you that, okay? And so I have, in this class, in this lecture, I have a lot of those. Anyway, so what is DECA NLP? Again, it's a multitask learning framework. Models must internally adjust. You cannot, like, basically assume that you will have different training methods for, or different training pipelines for different tasks. So you have like the same shared parameters and you use those parameters for different tasks. Key specifications, there is no task-specific modules or parameters, unlike traditional multitask learning where you have them separated. A single model architecture that learns for multiple tasks. Internal adaptation for separate tasks. So instead of using task-specific heads, the model must implicitly recognize the task. And the same model should handle the multiple tasks like summarization, QA, translation, NER, etc., without retraining. So everything is in the same set of parameters. It provides also zero-shot generalization for unseen tasks. If a model learns, say, for example, from 10 tasks, it should be able to explore or extrapolate to new unseen tasks. This answers the question that we had earlier here, and enables transfer learning. Okay, here's what we have. So this is like the architecture of DECA NLP. By the way, those are like delivered to you by my hands. So those are like actual boxes. I'll give you the BBTs, and like, I had to like replicate those one by one, and I not did them by one. I did this block and that block and this block, change the color, zoom them and whatnot. So and then, like, I felt proud of myself doing that. Yeah. back then. It took me a lot of time. I was learning PowerPoint at the time. So this was done last year, by the way. For a long time, I just copied the paper. It is in the paper, the same coloring. I copied the figure from the paper, but then I realized, like, I teach this class like 3-4 times. I should do them. Okay, so how does it work? The first step, start with the context. This is something that we already have. Provide relevant background information. Second step, ask the question. Print everything that you have, any text that you have is a question, and generate the answer word by word. Okay, and so PowerPoint. Yes, this is why it's tedious, right? Now you can use GPT or whatever that is, right? Yeah, banana or yeah, you can do that. This is like, in the old days, last year. I did not have the courage to use GPT. Now I can use it. All right, so generate the answers word by word. This is very important, by the way. So each word is selected using one of the following methods. You can swap between them. Point to context. So you have like a pointer, like a memory to context. So you extract words directly from the provided context, like word by word again. So you can kind of have those multiple heads pointing at different pieces of information. It could be the context, could be the question, could be just like random generation, for instance. And then you just generate words based on that. So point to context, so extract words directly from the provided context. Point to the question, so you can use words from the question, original question, and choose from some external vocab. Right? This is like true generation. Select a new word from an external source. And to be able to do that, you have to do some switching, pointer switching. So at each step, the pointer switch will decide which method to use for generating the next word. Okay, fair enough? So, I mean, I'll go over this one very quickly. So what you have here is that you have the question and the context, and then you use the embedding for them, and then you can do some independent encoding on top of the initial encoding, so that you have this unified kind of encoding for the context and unified kind of encoding for the question. Because the question is going to be multiple utterances and the context is going to be multiple utterances. So I have them in the same unified kind of independent encoding. And then for the encoding, use some alignments, because again, the learning is going to be on some generic data. And then you want to align the given context and the given question on that data. So you do some alignment on them. And then you move it here to do some what we call co-attention, dual co-attention. What does the dual co-attention does? It takes the aligned question, the aligned context, and then kind of mingle them together. That's what we mean by co-attention. Co-attention between the question and the context. You can imagine that the context itself is going to provide the answer. So you have this, what we call dual co-attention. And then on them individually, you see, like, we got we got them to be co-attended, and then you separate them to do compression. For this part, you can do compression. This part now is going to have some co-attention from the initial input, right? So this is you can imagine this is the context, and it's going to have some information from the given question, and similarly for the question, it's going to have some information from the given context. And then what you do is that you compress it. Don't ask me why. This is like a recipe, right? Like, how do we do pizza? Some Italian guy somewhere just like figured that out. Okay. No, it turned out to work very well. Make sense? Right? It turned out to work very well. Empirical business. Yeah, empirical business. And the number of tasks also empirical. And so after that, you compress, you have like then multi-headed attention. Why do we have multi-headed attention? Different heads will attend to different aspects. For example, this is going to be a generation task. So one head can attend to, say, for example, syntax. One of them can attend to semantics. Some of them can attend to coherence, whatever quality that you want to have. Okay, some of them is local, some of them are global, and whatnot. So you have those multiple head attentions, and those are feed-forward networks. Okay, and then you have the final encoding. This is going to be the eventual output, not output, like eventual. Remember this? We had something similar to this. It was called contextual embedding. Where did we have that? In translation, right? So all the slicing and dicing and combination of context and a question eventually is going to give you a representation. And that representation is going to be used for generation of words, word by word. Where from? From the question, from the context, from some external knowledge. Very simple, right? I don't have to speak too much about this. Very simple, right? This whole thing, do not worry about it. This is eventually what you have is that you have question attention, you have context attention, and then you have some external knowledge from somewhere. And then what you do is that you do this like the switching between them. And so you have a question pointer, you have a vocabulary pointer, and output distribution from those, like, you know, a context pointer, vocabulary distribution for outside pointer, and the question pointer. And then that's going to be combined to get you some output distribution, and then decode a word based on those combinations. Make sense? The distribution is feedback. Again, yes, because it's going to be the next word based on the given context that is in the output distribution. Similar to what we have done in LLMs, language modeling, right? Remember, in language modeling, when we generate a word, we are not generating a word arbitrarily. We are using the context so far, like the distribution so far of the generation, to decide the next word, right? And so this is, oh yeah, here. Okay, so it's a beautiful thing. Let's go over them one by one. By the way, here's an output example. So the question is here, the context is here, and then the answer would be given here. I'm just like, you know, showing you that it works. This is, by the way, snapshot from the paper. Let's go over it very quickly, one step by step, very quickly. Okay. So what we have here is we have the initial representation. What do we use for this representation? We use fixed glove plus character and gram embeddings, and then followed by a linear layer, and then shared by LSTM. This independent encoding is going to be a shared by LSTM with skip connections. This is what they use in this block. Then we add the attention mechanism, so the attention summation from the sequence to the other and back again with the skip connections between the aligned question and context. Then we have separate by LSTM. This self-attention transformer X2 is going to be separate by LSTM to reduce the dimensionality. 2 transformer layers, another by LSTM. Deep neural network. This is truly deep neural network. And then we have the autoregressive decoder. What does autoregressive mean? Yes, generate the future based on the current and past. Okay. So uses the fixed glove and character and grams embeddings and 2 transformer layers, and by LSTM to attend to outputs of the last 3 layers of the encoder. And then we have the LSTM decoder. These are like, you know, those probability distributions are the decoder, whether you generate from the given question, the given context, or external knowledge. Okay, so those are like the 3 distributions that we have: question pointer, context pointer, and vocab pointer. And then you combine that with multiplexing to get the output distribution and pick the current word. Okay, make sense? And then repeat up to halting. Any questions? Are we good? Okay. All right. So we will stop here, but then if you think about it, this is going to be trained, right? This whole spiel is going to be like mammoth. It's going to be trained. And then how do you start about training it? Imagine that you have multiple tasks that you want to train for, and you have, like, say, for example, NER and POS. You know what is POS? Part of speech tagging. Okay, POS. So that is part of speech tagging. Did you remember that? No? Oh, okay. No, I did not mean that one. I meant like part of speech, right? Okay. I should be very careful about my abbreviations. Part of speech tagging, okay? Part of speech tagging or NER. Like those are 2 different legitimate tasks that we have learned about. And what you want to do is that you want to train those jointly. Then you have data for this particular task, and you have data for another task. Start with some pre-trained model. Then the question to you, which task I should start with first? Like which one I should start optimizing my underlying model with first? That is what training and generalization try to address. You can start with the easy one, you can start with the difficult one. The difficult and easy is something that you can measure with the performance. For example, if with this data, this task required a long runtime. What does long runtime mean? It means that you have multiple rounds, multiple epochs of optimization of the parameters to reach a good loss. Okay, that's what it means. So if this is a difficult task, that means the required running time, then starting it with it first or last would make a difference. Okay, this is what we care about. So let's go over that. So something we call fully joint training. So you have the tasks, like you said, for example, task A, B, C, D, E, F. And so with the fully joint training, you have like multiple batches of data, And then for each like task, like we do not really distinguish between them, difficult, easy, whatnot. You can do like the first batch is going to be for the first task, second batch for the second task, third batch for the third task, and fourth batch for the fourth task. So you do them what we call fully jointly. Does it make sense? Okay. We are treating them equally in a sense. The first batch for the first task, second for second, third for third, and fourth. Okay, what is the problem with this? Anybody can tell me a problem with this? Say for example, task A is very easy task. And so a single batch will solve this task, right? Will optimize the model so it performs very well on this task. But then you have like, say for example, 1,000 batches. You know, we know that like, you know, the batches can be like 1,000, 2,000, 3,000, right? And so you go like multiple rounds and then you go back to task one, but task one does not require this additional batch, right? So you are over optimizing for task one when you do not have to, overfitting for task one when you do not have to. On the other hand, task E, for instance, can be a difficult task, but does not have its sufficient share of batches to do very well. Make sense? Okay. Any questions? Any questions? That's the problem with the fully joint training. All right, so that's why we have the anti-curriculum and pre-training. So a pre-training strategy that reverses traditional curriculum training, learning. So instead of starting with simple tasks and progressing to harder tasks, what you do is that the model first is exposed to complex, diverse data, and helps prevent overfitting to easy patterns early on, exposes the models to diverse data set first, gradually introduce simpler ones, and encourages robustness and generalization. So first, in this example, we start with the difficult one, right? So like, for example, the difficult one is going to be task one in this example, or task E, for example, task E. And then you fine tune for it with multiple batches, like rich amount of data, multiple batches. And then, go to the next more difficult, the next, and then you go to the easiest one. And so with the easiest one, you don't have to spend a lot of time. That's called anti-curriculum training. All right, so why use that? It improves generalization. It's proven. Improves generalization, it prevents local minima, and boosts performance on diverse real-world NLP tasks. Examples would be examples of this kind of approach of pre-training would include curriculum learning and anti-curriculum learning. Let's go over them one by one. Let's say that we have tasks, and in this case, A and B are difficult. C, D, E, F are not difficult, and so this is a decreasing order of difficulty, and the color signifies the difficulty of those tasks. A, B are difficult. So difficulty means how many iterations to converge in the single task setting. Make sense? This is what we explained. Then what we do is that we start like one of those is the curricular pre-training. Let's start with the easy one. Okay. The first one, the fully joint training, was you do not know any notion of difficulty. So you just like give them, everybody is equal share. It's a democratic system. Here with curriculum pre-training, we start with the easy ones. We train for the easy ones, another batch for the next easy, next easy, next easy, and that's it. Okay. And then you go to the difficult ones and you add multiple batches for the difficult ones. Make sense? Questions? This is beautiful, right? There is a problem here. Let me tell you the problem once I tell you the other approach. So the other approach is that you have, again, the decreasing order of difficulty. And so you start with the difficult one. You do very well in it. The next difficult one, you do very well in it. And then a batch 3, the difficult one, you improve upon it. And then the difficult one, you improve upon it. And then you do the easy ones. Make sense? So does it make sense? Good? Okay. What is the risk? What difference does it make? Like, what difference does it make that you are actually working on the easy ones first or last? Huh? Burnout? But you're not giving, like, okay, no. I'll say that I have 1,000 batches. And like, here, let's give me an example. 1, 2, 3, 4, 5, 6. I will give like 400 batches for the easy ones, and then 600 for the 2 hard ones. Okay, it's going to be 300, 300, 100, 100, 100, 100. Okay, so there is no burnout. I'll eliminate that reasoning. Okay, I'll give you the, anybody, any thoughts? Like, why starting with the more difficult one would be a more favorable choice than with the easy one. She said that, and we said no. We said go away. Sorry for that. All right. The answer is the same. No. Yes, go. Yeah.
The longest job.
Well, yeah.
I'll
I'll give a bonus point, 1 point. I think I'm going to generous like you. By the way, 1 point is raw point, so it means like 1%. If you are like B, you get A. It's like 10 points in our system. Okay, go. Give him the point. Yes, yeah. That's why it's generalization, right? Like, you know, we hope that if you like fine tune, what was that? It's something. Yes. So it's obvious actually. So the reason for that is because you know you deal with a difficult task, and the difficult task might have underlying it, and that is like result of the generalization. Difficult task over time would give you transfer to other tasks, and starting with a difficult one would allow you to kind of generalize to other smaller tasks. On the other hand, starting with a smaller task and then fine tuning for the difficult task might might result in what we call catastrophic forgetting. Okay, like the model will forget about this easy task. Okay, will forget about it. Okay, so okay, this is this. All right. You know, a couple of concepts before we wrap up. You know, in 3 and 4 minutes is what we have: zero-shot classification, and that can be done in question answering. So, what is zero-shot classification? A model ability to handle a new task without the explicit training for that task. It uses the question pointers to kind of reframe labels dynamically, adapt to variations in wording. How does it work? Or like, you know, how does the question pointers enable this zero-shot learning? Well, it has this flexible label representation that allows label variation. Positive means happy, supportive; negative means sad, unsupportive. You can just like, you know, change those labels, and no additional fine tuning required. And then natural language understanding can be converted to classification problems in this case. Example, the context: John had a party, but no one came and he was all alone. The query reformation as a QA is going to be, is this sad or happy? And the answer could be given. Huh? Yeah. I mean, yeah, that's true. I mean, you know, it doesn't matter. I mean, like, you know, can say like happy, he's happy. I mean, at the end of the day, it answers that, right? And though if you have like enough context about John, you will go to the like, you know, he's happy, right? Okay, so why this matters? It enables models to perform new tasks, can basically bridge the gap between classification, QA, reasoning, and moves towards general purpose NLP. Unified QA, so why frame them as such? A single QA model can generalize across multiple, enables more general language understanding. And so with that, you can track multiple NLP challenges, multitask learning, domain adaptation, transfer learning, weight sharing, and zero-shot learning. This is a summary. These are the results from the multi-Q question answering network. I'm not going to go over them in details because those are like just from the paper. And this is another result, and I finish. Any questions? Questions? Okay. Any questions online? Questions online? Okay. So another thing about the project. In the project report, I'm going to ask you to put an AI statement. I'll give you 0 in the reports if you do not have that AI statement. What does this AI statement state? So it states that if you use AI, like AI tools like ChatGPT, Gemini, whatnot, how you use them. You are not allowed, you are not prohibited from using AI tools for the reports. And in many cases, this is going to be mandatory because you're going to be working on, say, for example, testing an AI tool for your work. You can also use it for like fixing typos, but you have to be explicitly specific about how you use it. you use it for generation or whatnot. If you are confused about this and like, how you can use like AI tools for proofreading, talk to me. I have like a prompt for that. It's very, very specific. The prompt would say, you laughed. Athena, carry on. Why? Educating like, about legal things. So you have to be very specific, like, proofread this like text. Do not change wording, just like the proofreading, fix typos, fix grammatical issues, stylistic issues. Do not change ideas. Do not add new ideas. Do not generate. Do not deviate. Do not. Like, what you would say to your 17 years old son going to college. Do not drink. Do not. Yeah. Okay, make sense? Do not do what? I not tell him that yet. Yeah. I was doing like campus visit. By the way, are we good online? Do you have anything? Okay, we can stop the recording. All right. So I'll say something very quick. Stop the recording. Stop. Done. Okay.